There we go. Should be working. Let me check that it actually is working. Blah, 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 blah. Blah, 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 blah. Alright, gas. That's good. Take this, I'm gonna close that, I'll go over here. Bada bing, bada boom. Alright, let's do some physics. You guys can all still see my stream okay, right?
Yep.
Okay. You are moving into a new apartment, and your little brother said he would help. There is a ramp leading into the moving truck that is at an angle of 30 degrees, which has a static coefficient of friction of 0.5 and kinetic coefficient of friction of 0.3. While carrying a 10-kilogram box up the ramp, your brother gets tired and puts the box down on the ramp. What is the minimum force that your brother must apply to keep the box from slipping? Okay, so what I personally like to do for all my physics problems and just like this kind of stuff in general is drawing a picture is my favorite way to start anything. So I'm just going to draw, we got the ramp like so. We have our box, right? We know this angle right here is 30 degrees. We know this box is 10 kilograms. That's all readable still, right?
Yeah.
Okay. Gas. So our mu static is 0.5. Our mu kinetic is 0.3. And then we got, the dude here, and he's yeeting on this box. Okay, so we're trying to figure out what the minimum force that he needs to apply in order to keep the box from slipping. So we're trying to see, like, what do we need, if we'll call this box mass M, right? We want the force on M, the net force, that's an awful sigma. That's close enough. Net force on M needs to be equal to 0. So we got to figure out, what forces do we have on this box and what do we need to balance them out. So if we have this box right here, we can draw a nice free body diagram. We know that, like any object, it's going to have the force of gravity going straight down, right? And then because, of course, it has the force of gravity, it's going to have the normal force. But because it's sitting on a ramp, that normal force is perpendicular to the plane that it's on, right? So it's going to be facing this way. So we're going to have the normal force kind of going off here at an angle. This is force normal. And we know that there is friction in this problem, so we have the coefficient of static friction is 0.5. So because due to gravity, this thing's going to want to slide down the ramp, right? So we know friction opposes motion, so friction is going to be pointing up the ramp in this direction. And then finally, we want, okay. And then this kid, right, I'll label this force friction static. And then this dude, he's also pushing up. So we're going to have another force right here, and we'll call this F. I like F applied because it looks like it says FAP. So we'll write F app, force applied. So we got to figure out what combination of these forces, of known forces and unknown forces, do we need in order to get this to be static. So when it's like ramp problems like this, it's a lot easier to not have these all be off at weird angles. And if you only have your force of gravity off at a weird angle, it makes drawing it a lot easier. So because it's on a ramp, we can kind of redraw it so our normal force is pointing up. So we have our normal force pointing directly up, right? This means we're tilting the whole axis of the problem, because normally this is like x, y, right? And then we're redrawing it. So instead of like that, our axis is like this. So this is our normal force. We have force of friction and force applied. And then because we've tilted the whole problem, like the whole axis, right, our force of gravity is going to be going off like this. So we're trying to deal with these forces that are traveling to the right and to the left. So because we know the force of gravity, it's applying like this, it's going to have a component that's going out this way, and it's going to have a component that's going like straight down relative to this axis. So we can draw those on our free body diagram. You know, we got our y component, and we got our x component. And what's neat about when we draw it like this is we now know that because the normal force always acts perpendicular to the force of gravity, we can write, or let me label these, sorry. Okay, so this is our FGY, and this is our FGX. Right, so just looking at these, we can figure out what our equations are going to be, kind of. Because we know that this force of gravity here, the x component needs to balance out force of friction plus force applied. So we can write force of gravity in the x direction is going to be equal to force of friction plus the force applied. And then we also know our normal force is going to be equal to our y component. So we can write force normal equals force of gravity in the y direction. So now that we have these set up, we're solving for this guy right here, right? Force applied. So we got to get as many of these known quantities as we can. So normal force is proportional to the friction force, right? That's just the idea of friction, right? However hard you're pushing down on a surface is as hard as you're going to have a resistance. So we want to figure out what the normal force is, and we know the normal force is equivalent to this component of the gravity force. So we got to find the gravity force. So we can say that because we know this box is 10 kilograms times our handy dandy 9.8 meters per second, we know for a fact that 10 times 9.8 is good old 98 newtons is our weight. So in this triangle of weight here, where this is our force of gravity, we know that this arm, the hypotenuse of such, is 98, and we want to find our y component right here. And then we're all, oh, sorry, that's not supposed to be that. I might, wait, did I do something wrong? No, I didn't. Okay. Yeah. So then, yeah. So we're just focusing on the y component right now because we want to find our force of friction. So we can whip out handy dandy SOHCAHTOA. So if we know that this angle right here is 30 degrees, yeah, that angle is 30 degrees, right? Yeah, that angle is 30 degrees. Okay, and then we're solving for opposite. I'm really bad at trig, so if I mess this up, someone please correct me. Sine of 30 over 1 equals the opposite, so that's our force of gravity in the y direction over hypotenuse, which is 98. So 98 times the sine of 30 degrees. Am I in degrees? I am. Okay, so that gives us that our force of gravity in the y direction is 49 newtons. So we know that FGY is equal to force normal, so we can set both of these equal to 49 newtons. So normal force, 49 newtons, force of gravity in the y direction, 49 newtons. And then we want to find the friction force. So we know that the force of friction is equal to the normal force times the coefficient of static friction. And this value is just 0.5, and this one we just got is 49. So our force of friction is going to be equal to 24.5 newtons. So now we're one step closer to solving this equation up here for the force applied, because we now have the force of friction. So we just need to find what the x component is. So we go back to our triangle up here, and instead of doing sine to find the y component, now we're going to do cosine of 30 over 1 equals force of gravity in the x direction over 98. So cosine 30 times 98. I totally did this wrong because that's 84. God damn it. I did my trig wrong. Okay. Yeah, because this shouldn't be bigger than the y component. So we're going to go ahead and erase everything that I did. Oh, no, let me just go like that. There you go. Yeah. Okay, so our normal force is not 49 newtons. Our normal force is 84 newtons. If anyone has any questions of what I just fucked up, feel free to ask me. And then our force of gravity in the x direction is 49 newtons. I just did my trig wrong. Oopsies. 84.9. That's a good check too, is like when you're doing trig, like you should be able to intuitively realize that the force of gravity down is going to be more than the force of gravity to the side, right? Because it's like 30 degrees. So we can rewrite that as, right, it's going to be 84.8 times 0.5, which means our force of friction is going to be equal to 42.4 newtons. So now that we have our force of gravity in the x direction is 49, right, because we got that from our triangle, we can plug that back into this equation right here, and we can write out that 49, which is the only force acting this way, right, is going to be equal to force of friction, which we just solved for, which is right here, which is 42.4, plus the force applied. So if we just take 49 and we subtract our number that we got for our force of friction, we can solve that our force applied in order to make the net force in the x direction 0. Our force applied is going to be equal to 6.5, round that off to 6.6 newtons. So we'll pop that right here. Let me make sure I actually did that correctly. Yes, I did do that correctly. Beautiful. All right, so does anybody have any questions on that first one? Want me to go over?
Can you explain like where you messed up that first time?
Okay, so I have this triangle, right?
Yeah.
From up here, because our force of gravity is going down, right? So we got the force of gravity, and then I was figuring out the y component and the x component, and basically I just I don't think this angle is 30, like this angle is like 30 or something, and then basically I was using the wrong trig functions to find it. Yeah. So like when I was trying to find the y, I actually found the x, and when I was trying to find the x, I actually found the y. Right?
Okay, alright, I got it.
So like I was saying, just intuitively when you're doing like a ramp problem, it should be obvious that the force of gravity down is going to be applying more force than the force of gravity to the side. Right?
Yeah, okay.
Like, okay. Yeah, so if that's it for the first one, then I will continue on the second one. Yeah, so your brother gets even more tired during this process, no longer applies a force to the box and lets it accelerate down the ramp. What is the box's acceleration? So we already found a bunch of the things that we need to do this, but basically, since it's moving, we're just solving for what the acceleration value is now that it has a coefficient of kinetic friction, because kinetic friction is less than static friction. So we have our normal force value here, right? And if we want to find the friction force kinetic, we're just using our normal force, which was 84.8, except this time we're multiplying it by 0.3 instead of 0.5 because it's moving. Because we know it's going to be moving, so we can figure out what our kinetic friction force is going to be. So 84.8 times 0.3 means that our force of friction, kinetic, is going to be equal to 25.4 newtons. Yeah, and then we're literally just going to be figuring out our net force in the x direction. And the good thing about this is like we already did like most of the hard math. Like we know our force of gravity isn't going to change, right? Because the box's mass is the same. So it's literally just going to be 49 newtons minus the only force acting in the opposite direction is the frictional force, right? Now that we're no longer applying a force, minus 25.4 means our net force in the x direction is going to be equal to 23.56 newtons. Hopping good old Newton's one of the laws, F equals ma, right? We know our net force is 23.56 equals mass 10 kilograms times acceleration. So we divide that by 10, and that tells us our acceleration is going to be equal to 2.36 meters per second squared. Let me make sure I did that correctly. Yeah, I did that close enough to correctly. Yeah, and then our last question, this one's really easy. You're literally just plugging into the kinematic formula, right? Like delta x equals, we have no initial velocity, so it's just negative, oh, it's not negative, 1/2 a, which is 2.36 t 1.5 squared. And then if you solve that, that should be the right answer. What's that, 2.6, right? Yeah, like, okay, I rounded, but yeah, that's it. All right, so does anyone have any questions on any of these? Take that as a no.
No questions.
All right, gas. I realize this literally is not even a work problem, but you know, close enough. Does my stream still look okay? Oh, my stream is crunchy as hell, but literally is not even. Hey, it's still readable. All right, so let's go on to another one.
I mean, you could do a collision one, because I know I struggle with that one a lot. Which would be like
I
what?
mean, the next one in 6 is work, I think. I mean, I can go over that if you guys want me to. If you don't, that's fine. Like, does anyone want me to go over? Oh, you guys can only see my paint window, right?
Yeah. Work. No. In chapter 6, or I don't even know
6,
what
like
they call it.
one. I can go over this one if you want me to. If not, then I won't.
I don't think that's gonna be on the exam though, because it's 6.2 and onwards on this next exam.
All right. Well, Josue, being all fancy, knowing what's on our test, go off.
Because it's gonna start at power,
Oh, I see.
which is 6.2, and then
Oh,
everything
what?
past
That's
that.
not even. Oh, this is lecture 6.2. Oh, there aren't tutorial problems for 6.2 unless I'm really dumb. Yeah, no, there's not.
If you scroll down in the lecture for 6.2,
You know, that's it. That one I just copy and pasted is the last tutorial problem in 6.2.
We just reviewed today, and like a little bit of the exam, what's going to be a midterm, and we start at center of mass.
All right, well, I guess we'll start at center of mass then.
yeah. I mean, power is just force
Over
times time. I'm
distance.
pretty sure. Yeah.
Yeah. Oh no, sorry. Power.
Force times velocity.
Power is force times time. Yeah.
Or velocity, I think. That's. I don't know if I'm
That's
reading this
force.
right.
Watts is force times time, or force per time.
Yeah.
Like newtons per second is watts, which is power.
Yeah. Okay. I'll just send a screenshot of like the slide that has like the basic. Where's
Which one we want to do? We got the goalie one. I mean, the goalie one's pretty easy, I think. Like the car one. You guys don't know what I'm talking about, do you?
is that the one with the they stick together?
Yeah.
I feel like yeah, I mean, we can go over that. That's pretty fast. Those aren't that
Okay.
hard, I don't think.
Yeah. I guess let me put that bitch in snipping tool. Throw that baby in here. Bada bing. Bada boom. Shwing. Alright. Action. I love Paint. Paint's such a great program. Alright. Car with mass 950 kilograms and speed 16 meters per second approaches the intersection as shown in the sketch. A 1300 kilogram minivan traveling at 21 meters per second is heading for the same intersection. The cars collide, minivan collides, stick together. Find the direction and speed of the wrecked vehicle just after the collision, assuming external forces can be ignored. Wow, really just a car crash. Like, someone definitely died in this, and like these pedestrians are about to get hit, but you know, whatever. Okay, so this one's actually, it is pretty easy. You're basically just combining the momentums of the two vehicles. So we know this car down here, right, this guy, traveling this way at 16 meters per second, and it has a mass of 950 kilograms. Oh, 950 kilograms. So we just take those two numbers and we toss them together, right? And that's going to give us 15,200 kilogram in meters per second. Right. This guy down here, traveling this way at a speed of 21 meters per second and a mass of 1,300 kilograms. Throw those guys together. 1,300 times 21 is 27,300. And because these are getting applied, right, this one's just this way and this one's just this way, it's my favorite shape. It's a triangle. And we can use good old a squared plus b squared equals c squared to find what the magnitude of our resulting momentum is, right? So we take this number squared times this number, no, not times, excuse me, plus, so 15,200 squared plus 23,300 squared is a big ass number, and then you take the square root of that, and that gives you that our resulting momentum is 31,246 kilogram meters per second. That's the wrong unit, but whatever, you get the idea. So yeah, and then we know that our total mass, because it sticks together, is just the two of these combined. So M total is just equal to 950 plus 1,300. Direction and speed. Okay, so if we want to find the velocity, we can just take our momentum. Oh, sorry, momentum is p, right? And then divide that by the mass. So we know that it's this many momentums. Sorry, that many kilogram meters per second. So that number divided by our total mass, which is 900 plus 1,300, means our resultant velocity is going to be 14.2 meters per second. And then we want to find the direction, right? So we have a triangle with all these sides labeled. So we can just go like this. We're trying to find this angle, right? So we can just do tan inverse of opposite, right? Of where did this number go? Oh, that's, yeah, it's momentum. Okay, my bad. Yeah, so tan inverse of 27,300 over 15,200. pop that baby in the old TI-84. 15200, close, and that's going to give us an angle theta of 60. And that's our answer right there. We know this is 14.2 meters per second at an angle of 60 degrees, or 60.9 degrees from horizontal. That's it. Anybody have any questions on that one?
For velocity, what was it? I'm confused what P over M is.
Okay, so P is the total momentum, right? Because when we have like these triangles, right, this is because there's no external forces, okay? So all of the momentum from this car and all of the momentum from this car are being conserved because they're both going in independent directions. Like there's no momentum from here going directly up that's going to get canceled out by a car going this way. So we can just calculate the momentum of this car, which is 27,300. Calculate the momentum of this car, 15,200. And we can just draw a triangle with those. And we know when we add an up to a right, we're going to get a line that goes like this. So all we're doing is just using Pythagorean theorem to find what the momentum would be this way. And all momentum is just like amount of stuff times the speed of which the stuff is going. So if we have this number of momentum and we divide it by kilograms, all we're left with is meters per second. I hope that makes sense. If that does not make sense.
Yeah, makes sense. And then you're just dividing by the total mass?
Yeah, because the total mass, these two things are stuck together. So this now we can treat as one mass.
Okay.
Alright. Gas. Ooh. I'm going to go get a can of seltzer. Give me 10 seconds. That shit's good. Polar seltzer is honestly my favorite. So I'm good.
I hate seltzer.
Oh, yeah. I got a seltzer here. I got cranberry lime.
Oh, okay, good.
I don't know, man. Seltzer just has like a weird flavor to me. Like it's not strong enough for me to.
No,
enjoy.
I don't like most seltzers. Polar's the only seltzer brand I drink. All the other ones are actually just like ass.
I don't know. I can drink any seltzer. I just like seltzer.
LaCroix is terrible. LaCroix is awful.
Bro, I tried LaCroix and like the flavor is barely noticeable. It's just static water.
It's like water that has had somebody explain the concept of fruit to it. Oh, I actually don't know how to do this. Maybe we should do this one then. Okay. Excuse me. I don't know if anyone actually heard that, but I excuse myself regardless.
Bless you.
That was me burping, but you know, I guess that's close enough, right?
I say bless you anyways.
I guess that makes sense. Okay. A 70. What's 70 kilograms of penetration? Okay, that's a respectable 30 kilogram dog. That's a. I guess that's reasonable. Actually, I don't really know what dog sizes are. Okay. Oh, this is center of mass. Okay. Is everybody back?
What do you?
Oh, you didn't leave? Never mind.
Yeah, I'm just muted so I don't like make background noises while you're explaining it.
Okay. I mean, you don't have any background noise, but you're good. You're good.
Yeah,
You're good.
case.
Okay. Yeah. Okay, so center, we're finding the center of mass of the whole canoe system, right? So the center of mass is just equal to, excuse me, M1, so how much a mass weighs times how far it is from our reference point. And then we sum up all those. Oh, sorry, that should be a 2. The sum of all masses and their distance over a total mass. So in this scenario, we can kind of we can kind of just like rewrite this because this picture is kind of bad. So if we just draw this as a line, right? Oh wow, that is a really straight line. Nice. And we know this whole line is 5 meters long. In our first scenario, we have the woman here, so our M1, so 70 kilograms. And then we also have the dog on top of it, which is another 40. And this distance is 1 meter. And then right smack dab in the middle at 2.5 meters. Everything's drawn to scale here, as you can see. We got our 40 kilogram canoe, which is where the center of mass is. Does anyone actually need me to go over this? Because I feel like this is pretty easy. If someone wants me to, I totally will.
I'm good with this one. I've saw this before.
Yeah, center of mass isn't really that hard for me, but I'm not sure about everybody else.
Yeah.
I mean, I wouldn't mind.
Alan? Okay, I'll do it for Alan. I'll do it for Alan. Alright,
Yeah.
so we're trying to find the center of mass of the canoe, right? So, like I said, we're just summing up all our masses and our distance. So our first mass is the woman, which is 70 kilograms, times 1 meter, plus our dog, which is 40 kilograms, times 1 meter, plus our canoe itself, which is, dog is 30 kilograms, 30 kilograms times 1 meter, plus the boat, which is 40 kilograms, times 2.5 meters. And then all of this divided by the total mass, which is 70 plus 30 plus 40. So if we do this out, we get 70 plus 30 plus 40 times 2.5 divided by 70 plus, oh, that's it, 0, divided by 70 plus 30 plus 40, which means our center of mass of the whole canoe woman dog system is at 1.43 meters. And you can kind of like see that intuitively, right? Because like you have a bunch of mass over here and you have a little bit of mass over here. So it makes sense that the center of mass would be like here. That makes sense?
Yeah, thank you.
Alright. Beautiful. Alright. The dog moves from the woman's lap to a seat 1 meter from the other end of the boat. How much has the canoe moved during this event? Huh. I actually have no clue how to do that.
Wait, which part?
The B? Is
Oh,
that
it
just
says the
like,
dog lap to seat 1 meter in the boat where the woman stays.
is that momentum?
No, this is still center of mass.
Is it?
Yeah. Now it's just gonna, the center of mass is gonna change because the dog moved, and so his mass is now on a different x value than before, I think. Yeah, I can send. Okay, yeah. Let me.
I'm looking at the tutorial answers right now.
Basically, yeah, they have another variable xcf.
Oh, it's just what's the difference in the center of mass?
Yeah.
Oh, okay. Oh, I see. That makes sense. Okay. Okay. Yes, I'll do one out. All right. So basically, and back to my line. That line is not as straight. Instead of having the dog here, we still got our 70 kilogram. We still got our 40 kilogram, and now we have our 30 kilogram over here. So we can just find the new center of mass. If this is at 1 meter, this is at 2.5, and 1 meter from the other end of the boat. So this is going to be at 4 meters. Excuse me. Okay, so 70 times 1 plus 40 times 2.5 plus 30 times 4. Yeah, and that's all divided by 70 plus 30 plus 40. Throw that bad boy into the calculator. We get 30 times 4. 290 divided by 70 plus 30 plus 40 gives us a new center of mass final is equal to 2. I'll call that 0.07. So 2.07, that's a 7, minus 1.43 gives us a movement of 0.64 meters. And that's pretty easy.
Yeah, I don't know why they did it the way they did in the tutorial problem. Like,
Yeah, that's
just makes
a lot of math.
Yeah, where you can just calculate the two of them and find the difference.
Yeah, exactly. Let me see. This is right. The last one's just momentum.
Dog says take a swim. I think so. Yeah.
Yeah, it's just the dog jumping off. Okay. So if you got the boat here, right? Or does anyone have any questions on this bit right here? B. Going once, going twice.
Oh, wait. So, just the difference. That's why it's 4.
Yeah, it's just the difference in the center of mass calculating the dog moving to the other side of the boat.
Okay.
Alright. Yeah, so the last question, did someone just unmute or someone? Oh no, that was just Alan remuting. Okay. So then the final question, basically, we're just trying to find out how fast does the boat move this way if the dog, I'm going to draw a little doggy here. This is a great dog. Okay. If the dog jumps off the boat at 1.5 meters per second. So this is to momentum, right? Because momentum is kilograms times meters per second. So when the dog jumps off the boat, whatever his momentum is, which is going to be equal to his mass, so mass of the dog times velocity of the dog, is going to be equal, because equal and opposite forces, right? It's going to be equal to mass of the boat times velocity of the boat. And 3 of these are known values, right? So we know the mass of the dog is 30 kilograms. We know he's jumping off at a speed of 1.5 meters per second. And that amount of momentum is going to be transferred into the boat as well. So it's going to be equal to the mass of the boat, which is now just the woman and the boat. So 70 plus 40, so 110 kilograms times whatever the velocity of the boat is going to be. So we can find the momentum of the dog by just doing 30 times 1.5, and that's 45 kilograms times meters per second. That's once again not how you write that unit, but you know. And then we're going to divide that by 110 kilograms, and that's going to give us the velocity of the boat is going to be equal to 0.41 meters per second. And I'm pretty sure that's the right answer, and yes, it is. Okay, so anyone have any questions on that last one?
None.
No, yeah, I'm good.
Beautiful. Beautiful, beautiful, beautiful. Whew. I haven't talked this much in a long time. Let's see. I feel like, I don't know, that's a lab. Alright, so 8. Tutorial 8.1, let's see what we got. Oh, should we do the Super Bowl problem? I think we should do the Super Bowl problem. Yeah, let's do the Super Bowl problem. This is a good one, actually. I actually was like getting into this, and they cut our breakout room short. I was kind of pressed, not gonna lie. Let me just We're gonna need a lot of room here, so go like that. Yeah. Alright, I'm gonna resize this to 200%. That looks fine, right? Yeah, okay, guess. Alright, so super ball. A super ball of mass, 250 grams, is thrown straight up in the air, starting from a height 1.2 meters above the ground. Ball reaches its maximum height, 4.8 above the ground. After the ball hits the ground at point C, it bounces back from the ground point D up to a new maximum height equal to 2/3 of y max. So we have a bunch of variables here, and once again, I find that it is always very helpful to just draw a new picture, labeling everything you can. Right, so we have our, I'm going to rate, this is our scale, this is our height scale, right? So our initial point, we know is 1.2 meters, right? We know our ball is equal to 250 grams, which for the sake of math, I'm going to write as 0.25 kilograms. We know it gets yeeted up into the air, and it reaches a maximum height up here of 4.8 meters. It then falls back down to the ground. Down here, this is point B up here. Falls back down to the ground at point C. Yeah, and then it bounces back up to point C. Okay, sorry. C is the point just before it hits the ground, so I'm going to erase that. I'm going to erase this. Right, because it's hitting the ground down here. This is point C, and this is point D. So I wrote them with a little space, but just remember when we're talking about point C and D, C is the instant just before the ball hits the ground, and D is the instant immediately after it leaves the ground. Yeah, just remember that. So we got E, which is where it bounces back up, and that's at 2/3 of y max. So using advanced mathematical skills, we can find out that 2 divided by 3 times 4.8 means that the height at point E is 3.2 meters. And then it comes back down, you know, it does its thing. So what, oh wait, hold up. Yes, and this intermission on the ground where it's bouncing takes a total time of 0.4 seconds. All right. Any questions like the setup? This all makes sense where I got all the numbers from.
Yep. Yeah, that makes sense.
All right, gas. All right, so magnitude of the initial velocity of the ball when it was released at point A. So this is an energy problem, right? We can tell because we don't have any, excuse me, I'm gonna be burping a lot because I'm drinking seltzer, but we don't have any initial velocities, right? All we have are masses and heights. So, you know, this is all about kinetic and potential energy. So let's just keep in mind, right, the kinetic energy of an object is equal to 1/2 mv squared. And the gravitational potential energy of an object is equal to mgh. So kinetic energy, how much movie energy it has, is equal to its mass times its velocity, right? Those make sense, right? How much thing you have moving and how fast it's moving is how much energy it has. Potential energy, gravitational, right, makes sense. As you pull something up, you're adding more potential energy for it to fall. So that's just equivalent to its mass times the gravitational constant, because that's always the same. You know, if you're on the moon, it would be different. And then how high, right? Those are all relating to how much gravitational potential energy that thing has. So if we're trying to figure out the velocity here, we don't know how fast it's moving, but we know how much energy it has at the end. So we can figure out that when the ball was being thrown initially, I'm just going to be writing over these questions because there's not enough room to do the math here. So its energy at point A is going to be equivalent to its potential energy, oh, that's an F, at point B. Except at point B, there is no kinetic energy because it's not moving. It's just chilling in the air, and this is where all of its kinetic energy has been converted into potential energy. So we can say that the potential, no, we can write this whole equation as just potential energy at B is equal to potential energy at A plus kinetic energy at A. And since we know the mass and the height at points A and B, we can figure out these terms and just be left with the kinetic energy. So the potential energy at point B is going to be equal to 0.25 kilograms times its height at point B, which is 4.8 kilograms, or meters. I've been talking too much. And we can plug that in the handy dandy charity fort. And that's going to leave us with a gravitational potential energy at point B of 1.2 joules. So now we can say that 1.2 joules is equal to the potential energy at A, and potential energy at A is equivalent to 0.25 times 1.2, so 0.3 plus the kinetic energy at A. So we're gonna do a little math here. We can find that 0.9 joules is equal to the kinetic energy at point A. And if we expand our little kinetic energy formula out, we have 0.9 joules is equal to 1/2 m, which we know is 0.25, v squared. So we can take 0.9, divide that by 1/2 of 0.25. Once again, if I'm going too fast or you don't understand something, someone please just chime in and stop me. But that means that we're going to have 7.2 is equal to v squared. And if we take the square root of this, we take the square root of this, we get our velocity is equal to the root. That's not the right button. Our velocity is equal to the root of 7.2. So our velocity is 2.7 meters per second. Let me make sure I did that right. No, I did not. Okay. What did I do wrong? What? I did that very wrong. I'm confused.
I think I don't know, but like I think that since at point B has no kinetic energy, you can just use the two heights when, because like initially it has kinetic energy and potential energy, but at point B it only has potential energy.
Yeah.
And so you can set 1/2 mv squared and then use the mass times gravity times the first height, which is does it give it to you? Y initial?
Yeah, it does.
Yeah, so y, yeah, 1.2. So then we just mass times gravity times 1.2 is equal to mass times gravity times the y max, which is 4.8, and then you just can solve for velocity squared.
Isn't that what I did though?
I don't know.
I had gravitational potential energy is equal to potential plus kinetic.
Maybe did you use the right like heights?
I think so. Oh my, yeah. I forgot G. I forgot, yeah, okay. I forgot G. Okay, so yeah, what I did 0.25 times 4.8. I meant to do
times 9.8 as well.
4.8 times 9.8 times 0.25. Yes, that is what I did wrong. That's why my answers are wrong. Okay, so to clarify, here you can see I did mass times height. It is mass times gravity times height. Don't forget your G's, kids. So this is actually 11.76 This is 1.2 times 0.25 times 9.8. This is 2.94. That minus that is 8.82. And then if you do this math properly with 8.82 divided by 0.5 times 0.25, you get, this is supposed to be like 70, and then the root of 70.56 is 8.4 meters per second. Yeah, okay. So does anyone not understand what I did wrong? I just forgot to use gravity. I forgot the G when I was doing this, but yeah. Okay. So that I'm on with the problem. For part B, what is the change in kinetic energy of the ball due to the collision of the ball with the ground? Okay, so once again, this is actually like a really straightforward question. So we know that up here at point B, it has how much? It has 11.76 joules of energy, right, at point B. And then it goes down, and it loses some of its energy in a not perfectly elastic collision, right? And then what energy is left is what propels it back up to point E. So if we take point E, we know the ball, this is where it once again has kinetic energy of 0. So we can say that the energy at point E is equal to 3.2 times 9.8 times 0.25. That is insanely messy, but it's good enough. Say that at point E, it has 7.84 joules, and then all you do is just 11.76 minus 7.84, which is 3.92 joules of energy. So we can say that that is how much energy it lost, because that's the difference in energy before the collision and after the collision. That makes sense? Take that as a yes. What impulse did the ground impart to the ball? So impulse, that's what, J, right, is just equal to force times time, right? So we know this, wait, is that, hold up. Yeah, sorry, that's right. So impulse is just like how much force is being imparted over an amount of time, right? So we know that the impact lasts for 0.4 seconds, and the net energy loss is, oh god, my brain is melting. Give me 2 seconds. What? No, it's not that simple. My bad. Okay, yeah. Okay, sorry. I got this. Alright, so impulse is equivalent to the change in momentum, right? And momentum is mass, so it's equivalent to the change in mass times velocity. So if we find the momentum at point C just before it hits the ground and the momentum at point D just after it hits the ground, we can find the change in momentum. So in order to find the momentum at point C just before it hits the ground, right, just before its impact, we can use the energy, since we know that that the instant before it hits the ground, all of this potential energy has been converted into kinetic energy. So we can say that, once again, k equals 1/2 mv squared. We want to find our velocity. So we can set 11.76 equal to 1/2, mass is 0.25 kilograms, times v squared. Do a little mathematics. Divide 11.76 by 0.5 times 0.25. Take the square root of that number, and we get that our velocity at point C, or the instant just before it hits the ground, is 9.7, which means our momentum at point C is equal to 9.7 times, 9.7 meters per second times 0.25 kilograms, which is equal to 2.42. My voice is dying. Kilograms times meters per second. And we got to do the same thing for point D, and we know that afterwards we have 7.84 joules of energy, so we can do the same thing. 7.84. I'm not going to do this math out again because I just did it, so I'm just going to gloss over it. 7.84 divided by 0.5 times 0.25. And take the square root of that number. Our velocity at point D is equal to 7.92 meters per second, and then that times 0.25 is equal to 1.98 kilograms meters per second. And then we're going to take the difference between these two numbers, right? And that's going to give us a change in momentum of 0.44 kilograms times meters per second. So our delta P, or our J, is equal to 0.44 kilograms meters per second. Is that, what's the question even asking? Yeah, I think that's right. What? Looks like I'm off by a factor of 10. I'm actually very confused by that. What? Did I forget gravity again or something? What? What? Alright, I actually have no idea what I did wrong here. The answer is supposed to be 4.4 kilograms times meter per second.
Yeah. I might do this out one real quick, actually.
I probably just missed a zero somewhere. Because that's the right number, it's just off by a factor of 10.
Yeah. Let's do this. No, I got the same velocity you did.
Yeah, right? Like,
You multiply that by the mass to get the momentum, which is 2.43. Yeah, which is about what you got. And then do the same thing.
they might have actually just did it wrong. Oh, is it because you gotta multiply by time?
No, I don't think
No.
it has
Oh wait, no, yeah, time has nothing to do with that. Never mind.
It has to do with average force.
Yeah.
Time. Hold on. 0 times 9.8 times, what's the 2/3 max height?
Oh, 2/3 max height is 3.2 meters,
3.2, cool. And then,
which is 7.84 joules, right?
yeah, times 2, 0.25. Square root of that. Yeah, 7.92. That's what you got, right?
For
momentum,
yeah,
too.
well, that's velocity.
Yeah, for the velocity, yeah. And then
Yeah.
that times 0.25 is 1.98.
Yep.
Yeah, I don't know. For some reason they have a negative sign. Negative.
I think they did it wrong because an impulse of 4.4 kilograms meters per second, like times the 0.25 kilograms would mean a velocity change of 17.6 meters per second, which is more than either of the velocities.
Yeah. Probably a
Alright,
typo.
we're gonna call this answer good enough. It might be wrong, but yeah.
But the last question is really easy.
Yeah, it's literally just this divided by
The time, 0.4,
yeah.
which is just a 1.1, which is, off by a factor of 10 because for some reason theirs is 10 times bigger. It's not like a unit change or anything, right? It's not like in kilometers or something.
No, I think they actually straight up just did it wrong. Um,
Yeah.
Hey, I actually have to go to class in a bit. This is all like recorded on the live session, right?
mhm. It should be at least.
Okay, cool. All right, thank you.
Yeah, all good. Oh god, I've been going for an hour. Alright, to be honest, I don't know how many more of these I could do before I keel over and die.
I mean, I low-key gotta go soon too, so we can just call it a day.
Alright, yeah. I'm also always more than happy to explain shit to people in general.
Yeah.
Alright. Well, I'll